Evening, my name is Yahel Valdez-Rodriguez. Today I will be presenting lab number 6. My lab partners were Samantha Arellano and Braulio Silva. For our introduction, in today's lab we will study movement in 2 dimensions. There will be a steel ball launched from a cannon and we will measure the measurements with a meter stick when it lands on the floor. Where can we use it outside the lab? This can be used in fields like engineering, physics, or even sports when predicting and controlling path of moving objects, like for example, when planning rockets like an aerospace engineer, or vehicles like a mechanical engineer to better understand how gravity, velocity, and they affect the motion, or the concept of motion. Materials used in this lab will be a launcher, as in the first picture, it is a launcher. Our second, which would be a metal ball, which was already inputted into the launcher, as you can see that is circled in a black circle. And our third, which is a meter stick, carbon paper, and wild rolled paper. That will all be implemented into one. Here's a video of me pulling the trigger on the launcher as the ball launched into the paper. Braulio, on the other hand, was trying to prevent the ball from going out. This allowed us to better understand where the ball actually landed on the paper, as the carbon paper is used to mark on the white paper. So all of this is what, 100 centimeters? Yeah. Okay.
No. I was gonna. Yeah, I was gonna use the other one. Yeah. Oh, I was gonna use this one. The second one.
I already have it right here.
Okay.
In this video, you saw me and Braulio calculating the measurements of the initial position of the launcher, which was showed at the beginning of the video. We need to do some more.
Yeah.
This is just a short video of representing how the ball will land on the paper while the carbon paper was not implemented yet in the experiment. Our data analysis. In the first image, we see our first launch, which was at the 30-degree angle. Our second launch, which also have 5 points, which is a 45-degree angle, and our third launch, which is a 60-degree angle. All these were used when the carbon paper was implemented into the white paper and the ball was launched, marking them into the white paper. Here are results, or the dotted points are in meters. So now we have to find our data. For activities for lab number 6. For this lab, we will use the general second-degree equation in several presentations and solve for diverse elements as needed in each stop. For example, as you can see, is our final position, which equals 1/2 times the acceleration, times the time squared, plus the initial velocity times the time, plus initial position. Our equipment setup. In this experiment, the real challenge is to predict the final landing position of the steel ball at 3 different non-zero angles. Because the eye-hand reaction is reliable, we calculate our final time based on some of the initial and final positions. We need to start by knowing how fast the steel ball is the main launcher according to the range. We will set up either short or medium range. We call this the velocity, the muzzle velocity, which is VFM, and is the first value we will calculate. Here is a representation of the launcher. As you can see, there's 5 components into the launcher. Our first one is the metal weight. The second is the protractor. Our third is the launch point. Our fourth is the range setting, which was 30 degrees. 45 degrees, or 60 degrees, and our lanyard. Our table number 1 was the data to collect the muzzle velocity. For our x-coordinate, our initial position was x1, which equal to 0 meters. For our y-coordinate, it was y1, which equal to also 0 meters. Our y-coordinate didn't have, as there was no initial position for the y-coordinate, as it stayed in a certain length. Our final position was x 1.8554 meters. Our y was 0 meters. I also like to point out that the x was moving along the x-axis instead of the y, as it was not getting higher or lower, and it stayed at the same position. The initial velocity was v of x, which had to be the relative line, which was 4.38 meters per second. Our y component was 0 meters per second. Our acceleration was 0 meters, and our a times y equals to negative 9.8 meters per second squared. As you can see, this is our gravity. Our time, the middle step, equal to 0.424 seconds. How did we calculate this? By using the first equation I showed you in the first slide. Now we will implement the carbon paper onto the white sheet of paper. Then we will charge and launch our steel ball 5 times, measure and average the distances from protection of the launch point 3 on the floor. As like I said before, we had 5 landing points, and we had to find the mean by adding all of them up and dividing them by 5. Calculate the time and initial velocity in the x direction to what we call for now muzzle velocity, which would equal to t equals the square root of t2 initial y component over minus a of y. We have to be careful with the sign of our variables when doing the calculations. The formula above needs that you enter your acceleration as negative, so at the end we have a positive number inside the square root, which was v of m equals x of our final position over our time. This allows us to calculate the muzzle velocity. We will use the rest of the lab, which was 4.38 meters per second. Our spin and development. We had to set our main launcher to a 30-degree angle. Measure our initial velocity position of y equals 0. Using your muzzle velocity, calculate your initial velocity in each direction. We use the equation of v of x equals v of m cosine theta, and for our y component, we use v of y equals v of m sine of theta. We had to calculate our time of flight. In order to do this, we had to use the quadratic formula, which was t equals minus b plus or minus square root of b squared minus 4ac over 2a. We had to use a quadratic formula in order to understand the variables that we had to use in order to find the components that belong to each angle. To calculate our theoretical final horizontal position, we had to use x, our final position, which would equal to v of m, or cosine theta, times the time. We have to draw a horizontal line in the middle of the page on a black sheet of paper and write down a line at theoretical distance from the origin of the floor, measure our final position, and set the line of the page at that point. Take the page to the floor so it does not move. We have to place the carbon paper on top of our page and shoot the main launcher 5 times, like I said before. We have to measure the distance from our theoretical line to our landing points, average those values, and use them to calculate our percent error, which would equal our x of a of e over x, our final position, times 100. Now, we will table 3, which was our data, our final data, which was the landing theoretical values and percent error for different angles. For our 30-degree angle, we had the theoretical distance, which was 2.69 meters. For experimental differences, for 30 degrees was 2.67 meters. For a 45-degree angle, for our theoretical distance, which was the x component, final component, 2.64 meters. Our experimental differences, which was 2.58 meters. Our 60-degree angle theoretical distance was 2.12 meters. Our experimental differences for the 60 degrees, which is x a of y, was 2.05 meters, thus giving us a percent error of 7% for 30%, 45-degree angle, which was 2.27%, and our 60-degree angle, which was 3.8%. Our credits. Finally, we reach our credits. On camera, or the scientists, were Braulio Silva and myself, Yahel Valdez-Rodriguez. Our recorder was Samantha Arellano. Our calculations was Samantha, Arellano, and Silva. Who carried out the experiment was Samantha, Arellano, Silva, and me, myself. Our editor was me, myself, Yahel Valdez-Rodriguez. For our reflection questions or / our summary, for the first one, where do your percent errors come from? They come from the equation of the percent error, which was our x over acceleration velocity over our final x times 100. Now, if you go back to the slide, it would have to be the experimental differences, thus meaning that 2.67 over 2.69 times 100. For 45-degree angles, 2.58 divided by the 2.64 times 100, and then the 2.05 meters over the 2.12 meters for the 60-degree angle, which gives a 3.3%, as I mentioned before. Do you think there are still factors affecting your experiment that are not considered in the formula you were using? Yes, in some ways, as maybe some of the measurements were inputted wrong or they were slightly inaccurate to the actual value. To the actual value, I mean by the measurements weren't exactly the correct plotted points, but they were pretty close to the perfect position. Now, which ones? Maybe it was the starting point of the launcher. Maybe the starting point of the launcher was the one we weren't expecting, the perfect angle. Maybe we had a slightly different angle, except for like 31 degrees, or maybe it was 29 degrees instead of 30, or like for 45, maybe it was 47 degrees, or 43 degrees. And for 60 as well, it was probably 59, or maybe 61. Are they significant? Yes, as they can affect their percent error. Do you think there's a way to minimize that error? Yes, and that's to have more accurate or more perfect results on our launches, or more perfect results on our distance. Are all your percent errors equal? Why or why not? They can be equal because of the different angles you use for each try, and because of the different outcomes that happens in the launcher. Thank you so much for this lab report. I'm Yahel Valdez-Rodriguez. I'd like to give credit to Samantha Arellano and Silva for helping me implementing all this into the lab report. Thank you so much, and I'll see you in the next lab.